Okay, welcome to my Project Euler solution series. The next one we are going to focus on is problem number 3. Problem number 3 from here, projecteuler.net, is what is the largest prime factor of this number, which is a very big number. So the first thing I'm going to do here is copy this into my VI so I can reference it. Get this out of the way. And now we can start to break down this problem. So the first thing we need to do is generate an algorithm that creates a prime number and then checks whether this number is divisible by that prime number. Okay, that took me embarrassingly way too long to develop, but here's an algorithm that will now check to see if a number is prime. Let me walk you through what it does. So first I pass this number into a while loop, and I'm going to use this loop iteration counter. Now this starts at 0, so the first number I want to check against is 2. So that's why I add 0 plus 2. This, what will come out here is 2. So I take the number divided by 2 and check the remainder. Now there's two conditions that will end this loop. The first is as this loop counter, or as this loop iterates from loop to loop, this will go 0, 1, 2, 3, 4, 5, and so it'll iterate up through the numbers one by one, and add 2 to it and check to see and check and divide that number. If at any point any of those numbers in those loop iterations, the remainder of the divisor between the number to check and the current iteration number, if that's ever 0, then we have found a number that is evenly divisible, and therefore it is not a prime number. So if that's the case, this will end the loop through this OR statement. The other condition is if the number to check and the number that I'm dividing by are equal. That means that we have gone through as many iterations as we need to get to the number to check, and they are now equal, meaning that we are checking in the number divided by itself category. So if we're either dividing the number by itself, or we have found a divisor that is equal, that is divisible equally, then we need to end this loop. So if either of those cases are true, we'll pass in the OR, and then this will get passed into this while loop stop, and that will end the loop. Then to check whether or not that number is prime, all we have to do is see is if this loop ended because these were equal. If it ended because these were equal, then this will be true, and that means it's a prime number. We got all the way from 2 to the number to check, and that means it's prime. So to kind of check that here, I've got a few numbers to check. So 30 is not prime, 29 is prime, 28 is not prime, 27 is not prime, sorry, divisible by 9 and 3. 26 is not prime, 25 not prime, 24, 23 should be prime. So you can see this part of the algorithm works. Now, I'm going to do a couple of things. One is I'm actually going to make this section of code here a subVI, because I suspect that for other things in this Project Euler, I am going to have to check to see if numbers are prime. So I'm going to go up here into File, Edit, and I'm going to create a subVI. And what's happening is I'm creating a subVI from the parts of code that I have selected here. So I'm going to select all of this, Edit, Create subVI, and it's going to create this little guy right here. So I'm going to double click to open that VI. It opens up this window. I'm going to bring it over here, and I'm going to Control S, save this, but I'm going to save it under the subVIs. So I'm going to save this as check for prime number. And so now I have this little piece of code that will check, and it's nice and succinct. It's a little subroutine here that will check any number that I put in here, check and tell me if it is prime or not. The other thing I'm going to do, you can see on these controls and indicators, if I right click on one of these and you see this is checked view as icon, it gives this larger version of it that's called a LabVIEW icon, and I kind of don't like that. It's too big and it's unnecessary for me, so I'm going to click those away off of view as icon, and they're going to make these smaller versions. But I'm also going to go up to here and it's tools, options, and I'm going to change the block diagram so that when I create these things, I'm not going to create icons. I'm going to create them as the smaller versions of them. And I do that simply by unchecking this box right here. The other thing I'm going to do is adjust the normal location for these labels. So for controls, I want them in the left middle. And for indicators, I want them on the right middle. And what that's going to do for me when I save it is if I grab these and I do the diagram cleanup, oh, I got that wrong. Tools, options, bottom right, I want right middle, that one. When I do the diagram cleanup, which I can do by pressing this button up here or hitting Control U, it will automatically place the indicators labels on the left and the indicators labels on the right and the controls indicators on the left. I just like doing that because I think it's a cleaner way to do things. Okay, so I'm pleased to announce that took a lot less time than I was expecting. So you got to see a little bit of the development. Now let me walk through it. I'll start by saying one of the things that actually changed was I discovered that having this actually wasn't working. If you put 2 into the algorithm, if you put 1 into this algorithm, then it would cycle forever because it would never hit this equal point and it would never be divisible by 0. So I added this case where the first thing it checks is the number 1 or 2, which are prime numbers. And then if it is not 1 or 2, then it goes through this algorithm and checks if it's prime. So what I do is I do sort of the same thing. I start with, I pass this number into a while loop. I start with I equals 2 and check if that's prime. If the number is prime, I will execute this next algorithm, which I will explain in just a second. But if it's not, what I do is I just pass through and I skip that number. So I don't add anything to this array. Let me label this prime factors. And this is current number. If it is not a prime number, I don't add anything to these prime factors. This tunnel version here is called concatenating, which means it doesn't make a higher dimension array. It just takes and adds things to the array. So if I change this to tunnel mode indexing, then, and I delete this here and create an indicator. This double blue line means this is a 2D array. So if I index this, it takes this 1D array and creates a 2D array. But I don't want to do that. I just want to create a 1D array of all of these prime factors because that's what I'm ultimately looking for. So yeah, if the number that this iteration is currently on is not prime, then it goes into the false case and nothing happens. If it is prime, that's where we start factoring or checking to see if we can factor. So what we do is we take our current version of the number. Sorry, and by current, I mean if you follow this through, like this shift register, it ends up passing this number through this shift register all the way through. And if we find a number that it is evenly divisible by, then that number gets passed through so that the next version of the number is one that is divided. So that's what the shift register does. So if we find a prime, and we find, this is a very similar algorithm, that prime factor, that the number is divisible by that prime number, then we follow a very simple algorithm. We say, so in this loop, we take the number, we divide it by the current prime number, and we look at the remainder. If that remainder is 0, then it is evenly divisible. This select here is kind of like a little condensed case statement. If what comes into here is true, then this top number will get passed through. It's kind of like a switch. If it's false, then the bottom number will get passed through. So if this is evenly divisible, this will be a true. It will stop the while loop, and you can cycle back and forth between stop and run. So in this case, if I put a true here, it will stop. And if I put a true here, it will stop. So it's kind of the opposite case. So it will stop this loop. It will take the quotient and pass that through out of the shift register and back through the rest of this loop. And it will add the current number that I am dividing by. In fact, I should change this so there's less tunnels here. I'm going to change it to this number, so that's the same thing. It will take the current number that I'm dividing by and add that to my prime factors array. So what this is doing is it's telling me I found a number that is prime through this case structure, and I found a number that this number is evenly divisible by because it's equal to 0, and I'm going to add that into this array. So let me show you a little bit about how this works. I'm going to turn on highlight execution. I'm going to put a breakpoint right here, and I'm going to put a probe right here and right here. So what we are seeing now, I already ran this once, so let's run it again. What we should be seeing, I'm going to turn this off now, are a series of prime numbers and the current number that is on this register right here. So as we can see, I'm going to cycle through this by hitting the pause. which really means continue. And you can see here, I'm going to cycle through all of the prime numbers. Now, before I get to 71, which I know is a prime number, I am actually going to put another probe here. And you can see as I cycle through this, 67, 71 becomes a number that gets passed out here. Previously, it was always 0, but now I'm going to see 71 because I checked that it was evenly divisible by 71. And two things happen. One, something came out of this array. And two, this number got divided. It's no longer 600 million. It's now 600 billion. It's now 8.4 billion because I took this number and divided it by 71. So now the new number is 8.46269 billion. And so that number is what is now going to be passed through over and over. My number is 839, so I'm not going to actually cycle through and do all of that, but I'm going to actually remove my breakpoint and let this run to completion. And we can see that the array that I get out here is the same array that I got using the prime factors subVI. So the other thing that's interesting that I'm going to do is I'm going to compare this algorithm, the inbuilt one or the native one, to the one that I built. And to do that, I'm going to create a flat sequence structure. I'm going to add a frame after and a frame before. Add frame before. Now what a flat sequence structure does in LabVIEW is it forces things to execute in order. So what I'm going to do is I'm going to put this higher resolution relative seconds in here. Whoops. And I'm going to subtract the final time after this completes with the initial time before this completes. And I'm going to create an indicator. I'm going to say native VI execution time. Oops. Time. And I'm going to run this, and it should give me a time in seconds. So it looks like this took 0.237, so 237 microseconds to execute. And I'm going to do exactly the same thing on my algorithm. Add frame before, add frame after. I'll copy this in here. And I'm going to change it so that now I'm checking mine. David's VI execution time. Clean this up, find where it dropped it, and I'm going to run it again. And we can see that mine is significantly slower. So you can see here, this is taking on the order of 300 nanoseconds, and mine is taking nearly 100 times longer than that. So I'm sure this algorithm has obviously been optimized for finding prime factors. I don't know how it works. Oh, actually, I do know how it works. Here's the block diagram for it. It looks very similar to mine, although it's definitely doing something different here. I don't have any square roots and double computations or things like that. And so this is kind of interesting. It'd be interesting to look through here. There's some array operations going on. But overall, it is doing roughly the same thing, but it's obviously doing a more efficient computation. So that is finding... Oh, actually, we have one more thing to do. So the next thing, what it actually does is say, what is the largest prime factor of the number 600 billion, whatever. So in order to find that, we will use the... So in order to find that, we will use the array min and max, and we will take the max value of that array, largest prime factor. And we will see it here, 6,857. And if we look over here and check that with our random solutions, we can see that the correct answer is in fact 6,857, and both my algorithm and the LabVIEW algorithm prove that out. Okay, hope you enjoyed.